Hello again. This is Math 2233 coming to you from the College to page. The title of this lecture is Vector Cross Products and Torque, and I encourage you to be an active learner as you watch this video. By way of introduction, in electricity and magnetism theory, the current is the motion of electrons, and that has a velocity. And so that is a vector quantity. And it also induces a magnetic field, which you see here lives in the X and Y plane. And you see that the electrical field lives in the YZ plane, and together all this constitutes an electromagnetic wave. So these are vectors, each and all, and you see that all three of these vectors are perpendicular one with another at each point. The cross product of two vectors that are not parallel will be shown to be a vector that is perpendicular to both of the vectors. This product can be used to find areas and measures of torque. Here's three applications they're talking about. Torque is applied whenever a mechanic uses a wrench to turn a bolt. The magnitude of the torque is given by the magnitude of the cross product of the vector force used and the vector representing the wrench. An architect designing a bridge may need to ensure that the sides of the bridge are perfectly parallel. The cross product can be used here, as the cross product of parallel vectors is 0. And in a similar kind of architectural fashion, when building rectangular bricks, the edges of the bricks must be perpendicular to each other at the edges of the corners. Given two of the edges as vectors, the cross product gives the third edge that would be perpendicular to the other two. With that as motivation, then, we begin to discuss the cross product. So given two non-zero vectors, A equal pointy bracket A1, A2, A3, and B equal pointy bracket B1, B2, B3, it is very useful not only for the applications we talked about, but mathematically, to find a non-zero vector C that is perpendicular to both A and B. And so let's see what it would have to do. So we say let C equal pointy bracket C1, C2, and C3. And we're insisting that the dot product of C with A equals 0 and the dot product of B with C equal 0. So we know that this is the dot product of A with C, and this is the dot product of B with C. So this is two equations and three unknowns. But we can eliminate the C here by multiplying all the C3 rather, by multiplying all the way through the top equation by minus B3, and the bottom equation just by A3, and adding the two equations together, and we get this. So now we have two equations, and well, we have an equation then with two unknowns. And so we reduce that dimensionality. And since this is equal to 0, that means that one of these variables is a scalar multiple of the other, and you can compute what that scalar multiple is. And so you end up doing that calculation and can conclude that these are values that work. So C1 can be this, C2 can be this, and C3 can be this. And so that means that the vector that we're seeking is this expression. And this is what we define to be the cross product. So A cross B is the expression pointy bracket A2B3 minus A3B2, comma, A3B1 minus A1B3, comma, and this is A1B2 minus A2B1. End of pointy brackets. Now notice that the cross product, A cross B, of two vectors, A and B, unlike the dot product, is a vector. And for this reason it's called the vector product. Note that A cross B is defined only when A and B are three-dimensional vectors. Dot products are defined for higher dimensions, but not the vector product. In order to make this explanation easier to remember, we use the notation of a determinant, and you will recall that a determinant of order 2, we take the determinant of a, b, c, d, you get this expression. So you take this times this minus this times this. Multiply across the diagonals and subtract. And so, for example, if we define this, we would take 2 times 4 would be 8, minus a minus, 6 minus a minus is a plus, and you would get 14. Now, a determinant of order 3 or even higher can be defined in terms of second order determinants as follows. A determinant of order 3 is defined in this way. You can expand across the top row taking a1 times, and so you cross out that row and that column uses 2 by 2. Then it is minus a2, you cross out this column and this row, and you have this one, plus a3, and you cross out these, and it's this 2 by 2. And so we can calculate that. Now observe that each term involves a number a in the first row, and that I is multiplied by the second order determinant by the left-hand side by deleting the row and column in which that a sub I appears. Notice that the minus sign occurs in the second term, and this is an example calculation. If we are calculating the determinant of 1, 2, minus 1, 3, 0, 1, and minus 5, 4, 2, we use the formula and we will get negative 38. It can be a positive number or it can be a negative number. So this is the definition of A cross B then. You get the same answer. So what you do is A cross B is you list I, J, and K as vectors across the top. Use the same SIGN convention. There's going to be a minus sign here. And you place A's coordinates in this row and B's coordinates in this row. And that's how we do such a calculation. Okay, so if A equal pointing bracket 1, 3, 4, and B equal pointing bracket 2, 7, minus 5, then what is vector A cross with vector B? You know what to do. Let's see how you did. Okay, so for those of you who did this calculation correctly and got that this is pointing bracket minus 43, 13, and 1, congratulations. If not, find out what you did wrong and move on from there. Here's another problem for you to consider. If you cross a vector with itself, it says you get 0. Now this is not a scalar. This is the 0 vector for any vector A in V3. You know what to do. Let's see how you did. Well, this is going to be a determinant and 2 of the rows are identical, so when you do the calculation you get 0, and again realize this is the 0 vector, not a scalar 0. Now, we've constructed the cross product so that it would be perpendicular to both A and B. This is one of the most important properties of a cross product, so let's emphasize and verify it in the following theorem and give a formal proof. Now, you could say we already did that by construction, but we do it again. So the theorem is that the vector A cross B is orthogonal or perpendicular to both vector A and vector B. Okay, in order to show it's perpendicular, we're going to compute the dot product. Remember that if the dot product is equal to 0, then the vectors are perpendicular. So we take this vector dotted with A, and we do the calculation. Now this is a dot product, so this is going to be a scalar. You do the calculation, a lot of calculation, and you simplify and you get 0. This is the scalar 0. And a similar computation could show that if you dot A cross B with B, it's also equal to 0. So therefore, A cross B is orthogonal to both vector A and vector B. Now, if A and B are represented by directed line segments with the same initial point, we're showing it down here, so it's A and B like that, so, and you've got an angle theta in between them, between 0 and pi. Since the answer is a vector, it has to have direction. Now you know it's perpendicular, but it could be going up or going down. And so it turns out that the direction of A cross B is given by the right-hand rule. So if the fingers of your right hand curl in the direction of a rotation through an angle of less than 180 degrees, or pi in radians, from A to B, then your thumb points in the direction of A cross B. So here you would be pointing directly up from A cross B, the right-hand rule. Now we know the direction of the vector, and so the remaining thing we need to complete is a geometric description of what is its length. If you know it, you see it's completely characterized by its length and its direction. So here's the theorem that tells us that. If theta is the angle between vectors A and B, and it's between 0 and pi, then the magnitude of A cross B is the magnitude of A times the magnitude of B times the sine of theta in between it. Now, so what we're going to do is we're going to square this side, which is going to be, you remember that the square of this side is going to be the sum of the squares of the coordinates. Remember that the absolute value of the magnitude of b squared is v dot v. That's what we're using here. Then there's a lot of calculation. You have to expand all of these. I encourage you to follow all these calculations. And then you reorganize it to determine that it is this, and this can simplify to this because a dot b is magnitude of A, magnitude b cosine of theta. So I make that substitution. Then I can factor out the magnitude of A squared and magnitude of B squared. I get 1 minus cosine squared theta, and so that is going to be the sine squared theta. Now we take square roots, and we observe that the principal square root of sine squared is equal to sine of theta, not plus or minus, because sine of theta is greater than 0 when we're between 0 and pi. So we now have proven the theorem. So now we know the magnitude of the cross product. We already know the direction from the right-hand rule. Let's continue with our geometric characterization of A cross B. Since the vector is completely determined by its magnitude and direction, we can now say that A cross B is the vector that is perpendicular to both A and B, whose orientation is determined by the right-hand rule and whose length is magnitude of A, magnitude of B times sine theta. And that's in fact how physicists often define A cross B. So two non-zero vectors are parallel if and only if, in this corollary, A cross B is equal to 0. Well, it turns out that the only way that could be equal to 0 is if the sine of theta is equal to 0, and that's only true whenever theta is equal to 0 or theta is equal to pi. That means the vectors are parallel. And so that's how you make the if and only if proof. Another geometric interpretation can be seen by looking at this figure here. If we look at a parallelogram, the area of the parallelogram is going to be the base times the height. It's the same formula as a rectangle, except the height is this perpendicular projection that we talked about before. And so what happens is that the height is going to be magnitude of B times the sine of theta, and this side is the magnitude of A. And so when we do that calculation, we get that this is the area of the parallelogram. And so the length of the cross product A cross B is equal to the area of the parallelogram formed by putting A and B emanating from the same place and constructing the parallelogram associated with that arrangement of the vectors. Okay, so here's a problem for you to consider. Find a vector perpendicular to the plane that passes through the point P, which is parentheses 1, 4, 6, Q, which is parentheses minus 2, 5, minus 1, and R, which is parentheses 1, minus 1, 1. This is a problem I've given on a test before. You know what to do. We'll see how you did when we look at the next video. But now, in closing for now, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. Till we talk again, God bless you all.